Good morning. Today we see an example of single degree of freedom system with a periodic loading. Calculating this periodic loading using the Fourier series. We remember in the present video the single degree of freedom system is mass m subject of external force Pt, the mass m, where is applied an damping force and a spring force. So we can write in this case the equilibrium of force using the second law of motion. So the inertial force plus the damping force plus the spring force is equal of Pt. So finally m for the acceleration plus c, the damping coefficient for the velocity, plus k for the displacement is equal of t. We can define what is the periodic load. Periodic load is a force or dynamical stress that repeatedly identically at a regular time interval. In simple terms, if you measure the intensity and direction of this force over time, you will see that this graphical trend creates a pattern that continues to repeatedly indefinitely. Here, the main characteristic of periodic load P is the exact time required for the load to complete one full cycle before starting over. The frequency F, it is the number of cycles the load completes in 1 second, measured in hertz. It is the inverse of the period, so F is equal to 1 divided 4. Mathematical definition and force over time Ft is considered periodic if it satisfies this equation. So Ft is equal to F for the time t plus the period Tp. And here we can see the example of a period in engineering and structural dynamics. Period load is very common. Some example including rotary machinery, the vibration generated by unbalanced motor turbine or propeller. The hydrodynamic force, the regular impact of ocean wave against the pillar of platform. The pedestrian traffic, the rhythm pace of people walking on suspension bridge. There is the case of a soldier when made the resonance of bridge, and aerodynamic vortice, wind blowing around a chimney or skyscraper can create a regular air force that push the structure laterally in a period manner. It's possible to express period load in the form of Fourier trigonometric series. Each term of Fourier series represents an harmonic component. The response of system due harmonic loading has already been computed early. The response to each term of series is then merely the response of harmonic load, and by the principle of superposition, the total response is sum of response of each individual term, harmonic term. The response of system to period load is examined with the help of Fourier series, and the load and response term is expressed in terms of trigonometric series or exponential series. We can calculate this Fourier trigonometry series and the result using Python. We can remember the equation of Fourier series. In periodic function, Pt can express the by Fourier series in this way. Pt equal value at 0 plus summary of n1 to infinity n for coseno di omega 1 bar for t plus summary of n1 n equal 1 to infinitive for dn for seno di n omega or omega 1 bar for t, or in equivalent way in this equation 4, where n is the number of harmonic and bar is infinitive. Omega 1 bar is the first harmonic frequency of load function, is equal of 2π the period of load function Tp. Omega n bar is equal of n for omega bar. Tp is the period of load function. The coefficient at 0 and at bn we can express it in terms of pt because the sine and cosine function are orthogonally. So at 0 is equal 1 divided Tp for integral of 0 Tp over pt. N is 2 divided 4 Tp for integral of 0 to Tp over force pt for coseno di 2 n divided 4 Tp gram for the time t, where n is in value, integer value 1, 2, 3, n. The same for bn. And the orthogonality property of the trigonometry function we can then state it as following. So the integral of 0 to t of seno di n omega 1 bar for t for seno di m omega 1 bar for t in the t is equal 0 for m different of n, t divided for 2 for m equal n. The same for the coseno, and the integral of the 0 at t, multiply the coseno and seno is equal, the time t is equal to 0, where n m's are integer. When an arbitrary period load is being expressed in Fourier series in the form of equation 3 or 4, it is apparent that it consists of constant load, average load value represented by coefficient 0, plus n series of harmonic load of frequency n omega 1 bar and amplitude a n e pn. Now we consider a Python application, and we consider to develop with Python code using Fourier series and triangular function similar to this, where there is this triangular can repeat in the time. We can see the code Python. You can see by line by line, and in the line 8, 9, 10 import necessary import the external library to handle matplotlib. Import NumPy is import the NumPy library, which provides support for a large multidimensional function. Import plotting framework to create the visual graph. From SciPy point integrate import the quad function for SciPy, which perform numerical integration, calculate the area under a curve, essential for find Fourier coefficient. After define function curve 1, this function defines the base shape of a triangular way to calculate the offset or average value of define this curve, taking time t, period t big T, and amplitude p. If t is minor or equal of t big divided for 2, check if the current time is the first half of the period, the rising slope of a triangle. Calculate P1, calculate the rising line linear value. Else, if it is the second half of the period, the falling slope, calculate this value. And return the value scaled by 140, integrate this over one period, yield the A0 coefficient. After there is the curve, the function curve 1c. This function defines the mathematical expression needed to calculate the IN coefficient, the cosine term of the Fourier series. Here define in the line 26 define the function adding n, the harmonic number. In the line 28 calculate the fundamental angular frequency omega is equal to y divided 14. And after there is the if and else, identical to curve 1, generate the base triangular shape and return this value, the line 33, multiply the triangular way for the cosine di omega n omega t and scale it by 2 divided 40. Integrate this yield the IN coefficient. The curve 1s, the sine integrand. This function defines the expression for Bn coefficient, the sine term. Here define the function, we pass this value, calculate the omega in the line 40, calculate angular frequency, and after generate the if else the base triangular shape. And return this value in the line 45, multiply the triangular way by sine di n omega t and scale it by 2 divided t. Integrate this yield the Bn coefficient. After there is the main code, define a main function. T equal 10, set the peak amplitude of a triangular wave to 10. T is equal to 2, set the fundamental period of wave to 2 seconds, and print this value, the amplitude force in Newton and the period force in second. In the line 57, at 0, equal of quad, curve 1, 0, t, arc, tp. Use quad to integrate curve 1 from 0 to t. It passes the t and p as argument. And the f sub here set the error tolerance. It returns the integrate value of 2 at 0 and discard the estimate error into in the line 60, turn on interactive mode in Matplotlib, so the plot update dynamical without freezing the code. Fig equal of plot, create a figure window that is 10 inch wide and 12 tall. AN NP010, BN NP010, create 2 array filled with 0 to store up to 10 AN BN coefficient. T value, create an array of time value from 0 to 4 to full period with a step size of 0.5 seconds. Point. There is after there is the loops. where for n in range 1, 11 start in an outer loop where n represents the maximum, the current reconstruction. It runs from 1 to 10. For n in range, so in the line 73, 73 an inner loop to calculate the specific Fourier coefficient up to the current n. So in less 1, integrate the curve 1c to find the nf, then cosine coefficient and store it in array. Bn less 1, integrate the curve 1s to find the n sine coefficient and store it in array B. Output, create an empty array to store the reconstructed wave value for the current value of n. For x in enumerate t-value loops through every time point. T-value, x is in the index, t is the actual time value. C equals 0, S equals 0, initialize the sum of the cosine and sine component at the specific time t. For n in range 1, n plus 1 loops through all calculated harmonics, and in the line 84, 85, add the nth cosine term to the running sum of C, and in the line 85, add the nth cosine term to the running sum of S. Output is the sum of these two values, C plus add 0. After, there is the plotting of a graph. Figure this line 89, x equal of figure of add subplot, add and subplot to the figure in 5 row by 2 column grid, and determine the position 1 through 10. X plot the reconstructed wave against the time using the dot connected by line, and set the title of force in X, in Y in Newton. Add the unit measure, and so execution for 1 second to watch it built. Okay, save all this graph in file PDF called Fourier triangular function, and save. We can see the output of this Python code. You can see here there is the harmonic. In the case of n equal 1, is an harmonic curve, and after there is the case for n equal 2, 3, 4, and finally 10, when the reconstruction with the Fourier series give the triangular force, where in this graph the time in the axis X and the force in the axis Y. So we can see we increment n, the curve become up similar of a triangle. We can see also the mm, what is the difference between the different case for n equal 1, for n equal 3, finally in n equal 10. The line in magenta is the triangular value. So you can see the light blue line is very next to the triangular exactly for triangular force. Okay, thank you. Bye.